Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Hey guys! Today we're going to take a look at the mathematical operations addition, subtraction, multiplication, and division. These 4 operations serve as the fundamental building blocks for all math, so it is crucial to have a solid understanding to build upon. Let's dive in. We use addition and subtraction to solve many real-world situations. Addition and subtraction are simply the mathematical terms used to describe combining and taking away. When we add, we are combining or increasing. When we subtract, we are taking away or decreasing. As a reminder, the symbol we use for addition is a plus sign. The answer to an addition problem is called the sum. The symbol we use for subtraction is a minus sign. And the answer to a subtraction problem is called the difference. Essentially, addition and subtraction are opposite operations. One adds value and the other deducts value. One strategy for visualizing these 2 operations is to use a number line. We will use a number line to illustrate the following examples. Let's imagine a situation that involves the sale of popcorn. For this scenario, let's assume that you are trying to raise money by selling bags of popcorn, and you start with 20 bags. When your first customer arrives, they wish to purchase 4 bags of popcorn. This means that your remaining number of bags will decrease. We can represent this situation with a simple equation that involves subtraction. We started with 20 bags, and we decreased by 4, or subtracted 4. Our subtraction equation is written as 20 minus 4 equals 16. On a number line, we can represent this deduction by starting at 20 and then moving backwards 4 units in the negative direction. Each jump backwards represents subtraction by 1. Now let's say you started with 20 bags of popcorn and ended up with 6 bags left at the end of the day. You need to replenish your stock in order to keep up your sales, so you make 4 more bags of popcorn. How many bags of popcorn do you now have available to sell? For this scenario, since we are looking at an increase of bags, we will use addition. This situation can be described using the equation 6 plus 4 equals 10. You had 6 bags initially and then combined that amount with 4 more bags. Now you have 10 bags in all. On a number line, addition is represented by jumps to the right in the positive direction. Each jump to the right represents the addition of 1 unit. So in this example, we would be starting at 6 and jumping 4 units to the right. We can see that we land on 10. It is important to notice that when using addition, the order of the values does not matter. For example, 10 plus 30 is the same as 30 plus 10. The placement or arrangement of the values has no effect on the outcome. Both arrangements would equal 40. However, the same is not true for subtraction. Does 30 take away 10 mean the same thing as 10 take away 30? Clearly not. We can see that the order matters when dealing with a situation involving subtraction. The technical term for this quality is known as the commutative property. Essentially, the property is true for operations where the values can move around, commute, and the outcome of the expression or equation will not change. The commutative property applies to addition, but not to subtraction. Another operation that also shares the commutative property is multiplication. Let's discuss multiplication together with division, as we did for addition and subtraction. Multiplication and division are similar to addition and subtraction in that they perform opposite functions. The function of multiplication is to represent multiple groups of a certain value, whereas division is designed to show the separating or subdividing of a value into smaller groups. As a reminder, the symbol we use for multiplication is a times sign. The answer to a multiplication problem is called the product. The symbol we use for division is a division sign, and the answer to a division problem is called the quotient. Multiplication is essentially a convenient and time-efficient way to show what's called repeated addition. For example, if you need to fill 30 bags of popcorn and each bag requires 60 kernels, it could take hours to count up how many kernels you need in total by just using addition. A faster and more efficient way to make this calculation would be to use repeated addition. Instead of counting each seed independently, we would group them up and add the groups together. The calculation would then become 30 groups of 60. This grouping, for the purpose of repeated addition, is the multiplication process at its core. 30 groups of 60 is written as 30 times 60, which is 1,800. So 1,800 kernels are required to fill up 30 bags of popcorn. Both addition and multiplication are commutative because the order does not affect the answer. 30 groups of 60 gets us the same result as 60 groups of 30. Our last operation, division, can be considered multiplication's opposite. When we use division, we are essentially splitting up a large group into smaller subgroups. For our popcorn example, we can use division to answer the following question. How many bags of popcorn can I make using 1,800 kernels if each bag requires 60 seeds? This situation requires us to divide the large value, 1,800, into groups of 60. Each smaller subgroup will now represent a bag of popcorn. 1,800 divided into groups of 60 is represented as 1,800 divided by 60. In this case, the answer is 30. So 30 bags of popcorn can be made with our 1,800 kernels. As you can see, division is not commutative because the order of the values plays a crucial role in determining the answer. 1,800 divided by 60 is not the same thing as 60 divided by 1,800.
Hey guys, welcome to the Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8, so our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5, An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are 2 different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8. And that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, and welcome to this video on the properties of exponents. Working with polynomial, radical, and rational functions oftentimes requires us to perform algebraic operations with powers. Recall that a power is nothing more than a base that is raised to an exponent. So let's take a look at the properties of exponents that are used to simplify algebraic expressions with powers. The product of powers property applies to powers with the same base. When asked to multiply powers with the same base, simply add the exponents. For example, b squared times b cubed equals b to the 5th. This rule makes intuitive sense if you expand each power like this. B times B times B times B times B. Counting up the bases of B that are being multiplied results in 1, 2, 3, 4, 5. B to the 5th. Therefore, the general form of the product of powers rule is B to the m times B to the n equals B to the m plus n. The quotient of powers property also applies to powers with the same base. However, the rule requires the subtraction of exponents. Let's look at an example. B to the 5th over B cubed in expanded form would look like this. B times B times B times B times B all over B times B times B. Canceling out common factors of B from the numerator and the denominator would simplify to be B squared. The quotient of powers property allows a quicker, more efficient result. Simply subtract the exponent of the denominator from the exponent of the numerator. 5 minus 3 equals 2. The general form for quotient of powers property is B to the m over B to the n equals B to the m minus n. The power of a power property allows us to raise a power to another exponent. Once again, expanding an expression makes understanding the rule a bit easier. Suppose the power b cubed is squared. In expanded form, it would look like this. B times B times B times B times B times B. Using the product of powers property, or simply counting up the bases of B, results in B to the 6th power. The general form of this property is B to the m raised to the n equals B to the m times n. Expanding on the power of a power property results in additional tools that are used to simplify expressions with powers. For example, suppose the base of a power is a monomial with a coefficient and a variable. 3b to the 4th power squared expands to 3b to the 4th power times 3b to the 4th power. Rearranging the factors to group the coefficients and the powers with the same base, b, and simplifying gives us 3 times 3 times b to the 4th times b to the 4th equals 9b to the 8th. This is called the power of a product property and illustrates that the exponent of each factor in the base must be multiplied by the power outside the parentheses. The general form for the power of product property is b times c to the x equals b to the x times c to the x. The power of quotient property is similar in that the exponent of a rational base is multiplied by the exponents in both the numerator and denominator. Let's look at some examples. B cubed over c squared, all of that squared, expands to b cubed over c squared times b cubed over c squared. The product of powers property results in the simplified expression b to the 6th over c to the 4th. However, applying the power of quotient property directly is often more efficient. B to the third over C squared squared equals B to the 3 times 2 over C to the 2 times 2, which equals B to the 6th over C to the 4th. Here's another example. 2b over c squared d cubed expands to 2b over c squared d times 2b over c squared d, one more time, 2b over c squared d. Rearranging factors and applying the product of powers property results in 2 times 2 times 2 times b times b times b all over c squared times c squared times c squared times d times d times d. This equals 8b cubed over c to the 6th power times d cubed. If we were to apply the power of quotient property, it would look like this. 2 to the 1 times 3 times b to the 1 times 3 all over c to the 2 times 3 times d to the 1 times 3, which equals 2 cubed times b cubed all over c to the 6th times d cubed, which equals 8b cubed all over c to the 6th times d cubed. The general rule for the power of quotient property is b over c to the x equals b to the x over c to the x. As you can see, these rules are essential in simplifying expressions within our work with various algebraic functions.
Hi, and welcome to this video on measurement conversions. Converting between different measurements happens all the time, whether you're measuring solutions in a chemistry lab or putting together a recipe in your kitchen. For example, let's say you're baking chocolate chip cookies and you only have measuring cups that measure in 1 cup, 1/2 cup, and a 1/4 cup. But the recipe calls for 6 ounces of chocolate chips. How do you know how many chocolate chips to put in? In this video, we'll learn how to use measurement conversions to solve these sorts of problems. Let's get started. Let's start by figuring out our chocolate chip problem. Remember, we only have our cup measurements, but the recipe is asking for ounces. Well, this is where conversions come in handy. In order to figure this out, we need to set up conversion fractions. The first step in setting up conversion fractions is finding our conversion factor. A conversion factor relates one quantity to another. In our chocolate chip example, our conversion factor is 1 cup equals 8 ounces. Now that we know what our conversion factor is, we can set up our conversion fraction. When setting up these fractions, always start with your known value as your first fraction by placing it over 1, like this. 6 ounces over 1. We then multiply by our conversion factor, which we also need to turn into a fraction. When we do this, we want to pay close attention to which value we place in the numerator and which value we place in the denominator. Since we have ounces and we are looking for cups, we want to place our cup value in the numerator and our ounces value in the denominator, so that our ounces units will cancel out and we will be left with cups. There's 1 cup, has 8 ounces. We then multiply across and simplify. So our ounces cancel out, and we're left with 6 times 1 cup is 6 cups over 8. So there are 6/8 of a cup, or 3/4 cups is equal to 8 ounces. Notice how our ounces cancel out on top and bottom, and we're able to simplify the fraction 6/8 by dividing both parts by 2. This gives us our final answer of 6 ounces equals 3/4 cups. So we need 3/4 of a cup of chocolate chips for our cookie recipe, and can use our 1/4 cup measuring cup 3 times. Let's look at another example. Sarah is driving down a road at 30 miles per hour. How fast is she traveling in feet per second? This problem is a little different from our last one because it will require 2 conversions. We need to find our conversion factors for miles to feet and for hours to minutes. There are 5,280 feet in a mile and 3,600 seconds in an hour. So our conversion factors are 1 mile equals 5,280 feet and 1 hour equals 3,600 seconds. First, we write our known value as a fraction. Notice that this is in miles per hour, so we are going to write the miles part on top and the hour part on bottom. She travels 30 miles in 1 hour, so we'll write it like this. Now we want to multiply by our conversion factors. Remember, we have 2 different conversion factors, so we need to be sure to include both in this step. There are 5,280 feet in 1 mile. And we want to put the mile on bottom because we want our units to cancel out. And in 1 hour, there are 3,600 seconds. Again, we have our hour on top over here because we have it on bottom over here and we want them to cancel out. So when we multiply through, our hours cancel out, our miles cancel out, and then we can just multiply across. So we have 30 times 5,280 feet over 3,600 seconds. When we simplify, this gives us 44 feet per second. If Sarah is traveling 30 miles per hour, she is also traveling 44 feet per second. Let's take a look at one more example. Caleb is painting a wall that is a total of 96 square feet. How big is the room in square inches? In this example, we need to pay close attention to our units. We are measuring in square feet, which means our conversion fractions will look a little different. Our conversion factor for feet to inches is 1 foot equals 12 inches. However, if you think ahead, we are going to run into a problem in our second step. Let's go through our process as normal and see if we can figure out what to do once we get there. We start by writing out our known value. 96 square feet. Remember, we used conversion fraction, so we want to turn this into a fraction, so we divide by 1. Then we multiply by our conversion factor. There are 12 inches in 1 foot. Remember, feet needs to be diagonal to each other so that eventually they'll cancel out. But what's wrong with this conversion? Well, if you multiply the units out, you can see that we'll be left with feet times inches because one of our feet will cancel out but the other one won't. To fix this, we simply need to multiply once more by our conversion factor. Since we are working with square units, it makes sense that we would multiply by our conversion factor twice, or in other words, multiply by our conversion factor squared. Let's finish out our problem by multiplying it all out. Our feet squared will cancel out with both of our feet down here. So we're left with 96 times 12 times 12 square inches. When we multiply this out, we'll get an answer that is equal to 13,824 square inches. And that's all there is to it. This process will work for conversions between any 2 units. As long as you know your conversion factors, you can follow these steps and find your new measurement.
Hi, and welcome to this video on lines and planes. The study of geometry is very much language-based, meaning that there are countless terms, relationships, and figures with meanings that are dependent on an understanding of other concepts. It can get pretty confusing if the foundational terms are not understood. In this video, we're going to start with the most basic figures: a point, a line, and a plane. These undefined terms are described rather than being defined, and they support the definitions of all other geometric terms. To start off, what is a point? A point is described as a very specific location or position in a plane. The notation for a point is a dot, but that dot does not have any dimension, length, width, or circumference. A point is named with a capital letter, as in point A. A line is described as a path, as if a point was dragged or is moving. A straight line extends infinitely in opposite directions. A line is typically named by referencing 2 points on the line, with the line symbol above. The line notation has arrows on either end to indicate that they extend forever. Points that lie on a line are referred to as collinear. A plane surface has length and width and extends infinitely in all directions. A flat surface, like a wall, floor, or ceiling, can be imagined as finite planes where geometric figures, like points and lines, can be drawn. A plane is typically named with a letter in script or italics, plane M, or by naming 3 points that lie on the plane ABC. Using 3 points in the naming of a plane lends to the perception of a two-dimensional surface. Points that lie in the same plane are said to be coplanar. Planes that intersect do so at a line, and it is possible for 3 planes to intersect at exactly 1 point. Now that we know these basic components, we can build our knowledge with terms that incorporate them in their definitions. For example, a line segment is the portion of a line that lies between 2 points on the line. The 2 points are called endpoints and are included in the line segment, as are all the points that are in between them. A line segment with endpoints A and B would be referenced as line AB. A ray starts at 1 point and extends infinitely in one direction on a plane. The ray symbol has 1 arrow indicating the starting point and the direction of the ray. When 2 lines on a plane cross each other, they are referred to as intersecting lines. Intersecting lines on a plane cross at exactly 1 point. Because a line segment has length that can be measured between the endpoints, the exact midpoint of the segment can be determined. A point, line, or ray, or plane that crosses a line segment at the midpoint is called a bisector. Intersecting lines on a plane that cross at 90-degree angles, or right angles, are perpendicular to each other. Examples of perpendicular lines can be found on window panes or on door frames. Lines on a plane that never cross are called parallel. These lines are exactly the same distance apart at all points, like the double yellow lines on a road, or tire tracks of a car. A line that crosses 2 lines in a plane at 2 distinct points is called a transversal line. Transversal lines, in combination with special angle relationships, are used to determine whether lines in a plane are parallel. As you can see, it is essential to understand the relationships between the undefined terms of a point, a line, and a plane in order to strengthen and expand your understanding of other geometry concepts. It's important to review these frequently from the ground up to keep pace and to retain your knowledge.
Hi, and welcome to this review of the Pythagorean Theorem. We're going to go over how to use it properly and also go over some special triangles called Pythagorean triples that could save you some time when taking tests. So, let's get started. First things first, what is the Pythagorean Theorem? The Pythagorean Theorem is a squared plus b squared is equal to c squared. Now, this is used to find the length of a side of a right triangle when we know the length of the other 2 sides. The triangle has to be a right triangle, which means that it has an angle that measures exactly 90 degrees, like this one. The theorem is very easy to remember and just as easy to use. In the theorem, A, B, and C are the lengths of the 3 sides of the triangle. But which is which? Let's start by figuring out where to find A, B, and C in a triangle. To start, you can tell that you're dealing with a right triangle because you see this little square in one of the angles. That's the symbol for a right angle or 90-degree angle. And any triangle that has a right angle must be a right triangle. So now we have to decide where to put the 3 side lengths. The key is to start with C, which is always on the side across from the right angle. This is called the hypotenuse, and it's always the longest side. You may be asking yourself, if C is always across from the right angle, how do I tell which of the other two is A and which is B? It's a good question, and the answer is, it doesn't matter. Either of these two sides, which are called legs, can be used as A and then just use the other one for B. Let's pick 3 centimeters for A. And our B will be down here, and we know that's 4 centimeters. So this is what our theorem looks like when we have it filled in. 3 squared plus 4 squared is equal to C squared. Now we can just evaluate 3 squared and 4 squared, which means multiplying 3 times 3 and 4 times 4 to get the following. So now we have 9 plus 16 is equal to C squared. So, what's that? Little addition tells us 25 is equal to C squared. Now, here's where it gets a little tricky. We know that C squared is equal to 25, but we want to know what C is, not what C squared is. So, how can we get rid of that little 2? Well, we use the inverse or opposite operation of squaring something, and that inverse operation is the square root. Since it's an equation, whatever we do to one side of the equation, we must do to the other. So I'm going to take the square root of both sides. The square root of C squared is C. And the square root of 25 just happens to be 5. Look at that. It's always good to check our answer to see if it makes sense. Since we're finding C, it should be longer than any of the other two sides, and 5 is greater than both 3 and 4. Also, because of the triangle inequality theorem, which is something we'll get to in a later video, the hypotenuse must be less than the sum of the other two sides, which means 5 has to be smaller than 3 plus 4, which it is. So you might have noticed that the answer to this problem was a nice, neat integer, 5. This is actually kind of rare if we look at random triangles, but it's not rare in a math problem you might see on a test. It happens whenever a problem uses a Pythagorean triple. The triangle we just looked at is the most common kind of a 3, 4, 5 right triangle. The legs measure 3 and 4, and the hypotenuse is 5. Sometimes it will be disguised by multiplying all the numbers by 2, which means we would get a 6, 8, and 10. Or multiplied by 10, which means we would have a 30, 40, and 50 lengths. Or maybe any other number. You don't need to know this to solve a Pythagorean theorem problem, but it's a nice shortcut to save you some time or allow you to check your answer another way. Other Pythagorean triples include 5, 12, 13, 8, 15, and 17, and 7, 24, 25. There are many more, but these ones are the ones you will see most often. Of course, there are right triangles that aren't Pythagorean triples. Let's look at one just so you can see what the answer will look like. Once again, we're solving for the hypotenuse, the longest side, which is opposite the 90-degree or right angle. This is length C. When we plug in 5 and 7 for A and B, we get this. "25 plus 49 is equal to C squared." So let's add 25 and 49 to get 74, which is equal to C squared. Then we take the square root of each side and find out that the square root of 74 is equal to c. Now, even though 74 isn't a perfect square, this is the answer. If you take the square root on a calculator, you only get an approximation of the answer, which is about 8.60232526 forever. We can do this approximation to do our checks. It's greater than either of the other two sides, and it's less than the two sides added together. But when writing the answer, we should use the square root form.
Hello, and welcome to this video about using the quadratic formula. Today we'll learn what the quadratic formula is, when you use it, and how it's applied to find roots in quadratic equations. Let's start by talking about quadratic equations. A quadratic equation in standard form is written as ax squared plus bx plus c equals 0, where a doesn't equal 0 and a, b, and c are all real numbers. The quadratic formula is an algebraic equation that helps solve any quadratic equation. The formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. By substituting in given values for the variables a, b, and c, you can solve for x using the quadratic formula. Solving for x gives us solutions for the quadratic equation. These solutions are also called roots. Let's consider the quadratic equation x squared plus x minus 6 equals 0, and use the quadratic formula to find solutions for x. First, identify the values for the variables a, b, and c in the quadratic equation. Since the first term, x squared, is the same as 1x squared, the value for a is equal to 1. In the second term, x, the value for b is also equal to the coefficient of 1. And since the last term is negative 6 or minus 6, the value for c is equal to negative 6. Next, substitute the values for a, b, and c into the quadratic formula. So let's write out our quadratic formula again so that we remember it. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And now we're going to plug in our a, b, and c into this equation. So x is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 6 all over 2 times 1. From here, solve for x using the quadratic formula. So all we have to do is simplify. So we're going to leave the negative 1 right here for now and move on to this part. So we have the square root of 1 squared is 1 minus 4 times 1 times negative 6 is negative 24. So minus negative 24 over 2 times 1 is 2. 1 minus negative 24 is the same as saying 1 plus 24, which is 25. The square root of 25 is 5, so we have negative 1 plus or minus 5 over 2. And now we're going to break this part into two different equations. So we're going to have negative 1 plus 5 over 2. Remember, x is equal to this, so this is one of our values for x. So negative 1 plus 5 is 4, over 2 is 2. And then for our other value of x, we're going to do x is equal to negative 1 minus 5 over 2. Negative 1 minus 5 is negative 6, over 2 is negative 3. So the roots for this quadratic equation are 2 and negative 3. In the example we just looked at, there were two possible solutions or roots for x. Quadratic functions can have two solutions, one solution, or no real solutions for x. To figure out how many solutions a quadratic equation has, look at the discriminant in the quadratic formula. The discriminant is the portion of the quadratic formula that's beneath the square root symbol. It's the part that's read as b squared minus 4ac. When simplified, the discriminant can be a positive number, a negative number, or 0. and its sign tells us how many solutions the quadratic equation has. When the discriminant is positive, then the quadratic equation has 2 real solutions. When it's negative, then it has no real solutions. And when the discriminant is 0, then the quadratic equation has exactly 1 real solution. In the previous example, the discriminant was 25. Since it's a positive number, we know that the quadratic equation has 2 real solutions, which is what we found when we worked it out. Let's look at another example. Consider the quadratic equation 10x squared minus 9x plus 6 equals 0. And let's use the quadratic formula to find the solutions for x. First, we need to identify the values for the variables a, b, and c in the quadratic equation. Our first term, 10x squared, tells us that a is equal to 10. Our second term, negative 9x, tells us that the value of b is negative 9. And our third term, plus 6, tells us that c is equal to 6. Now we're going to use the quadratic equation to solve this problem. So our formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now remember, writing out formulas helps you remember it, so whenever you can, it's a really helpful thing to do. Now all we have to do is plug in our numbers for our variables. So negative b is negative 9, so be careful when plugging it in. You need to make sure you have the negative 9. Plus or minus the square root of b squared is negative 9 squared minus 4 times a is 10 times c is 6 all over 2 times 10, which is equal to minus a negative is equal to a positive. So we're going to have positive 9 right here, plus or minus the square root of negative 9 squared is 81. And then 4 times 10 times 6 is 240. So we have minus 240 all over 2 times 10 is 20. So this gives us 9 plus or minus negative 159 over 20. And we can stop right here because we see our discriminant is negative 159. Negative numbers don't have real square roots because a square is either positive or 0. So remember, if the discriminant is a negative number, then there are no real solutions to the equation. So we can stop right here. Our answer is that there is no real solutions for x. Now it's your turn. I'm going to give you a quadratic equation, and you need to use the quadratic formula to identify the possible roots for x. 9x squared plus 12x plus 4 equals 0. Pause the video here and try it yourself. And when you're done, resume the video and we'll go over everything together. Let's take a look at this one together. Start by identifying the values for a, b, and c. Based on the equation, we can see that a is equal to 9, b is equal to 12, and c is equal to 4. Next, substitute the values for a, b, and c into the quadratic formula. So remember, the formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we just take our numbers up here and plug them in for all our variables. So we have negative 12 plus or minus the square root of 12 squared minus 4 times 9 times 4 all over 2 times 9. So this simplifies to negative 12 plus or minus the square root of 12 squared is 144 minus 4 times 9 is 36 times 4 is 144 all over 2 times 9 is 18. So then we have negative 12 plus or minus the square root of 0 over 18. The square root of 0 is 0, so all we have is negative 12 plus or minus 0 over 18. And if you add or subtract 0, that's not going to change your number at all, so this is really the same as negative 12 over 18, which we can then simplify by dividing both the numerator and denominator by 3. So that'll give us negative 4 over 6. And we can simplify that one more time by dividing both by 2 to get negative 2/3. So x is equal to negative 2/3. And that's our root for this equation. Quadratic functions occur in many real-world situations. One example is shooting a cannonball out of a cannon. When you do this, it goes up and then it comes back down in the shape of a parabola. Since a parabola is the graph of a quadratic function, you can use the equation for the path the cannonball follows to answer questions about its time, speed, and distance. There are lots of other problem-solving instances in which quadratic equations are helpful. Understanding them helps us apply mathematical concepts in the real world. I have one more problem for you to try. Let's take a look at a word problem that we can solve by using the quadratic formula. A high school physics club shoots a model rocket into the air from 12 feet above the ground. The initial velocity of the rocket is 19 feet per second. The equation h equals negative 10x squared plus 19x plus 12 can be used to show the height of the rocket after x seconds. How long does it take for the rocket to hit the ground? We can solve this problem by applying the quadratic formula to the equation given in the scenario. This problem is a little bit more challenging, but I know you can handle it. Pause the video here and try it yourself, and when you're done, we'll go over it together. Let's take a look at this one. In this scenario, we are looking for the amount of time it takes for the rocket to reach the ground. The height, h, at ground level is 0 feet. Therefore, we can replace 0 for h in the equation. So we can rewrite it as 0 equals negative 10x squared plus 19x plus 12. And now it looks like our quadratic equation in standard form, just with our 0 on the left side instead of the right side. So now that we understand that our equation is really just in standard form, we can identify the values for a, b, and c. Based on our equation, we see that a is equal to negative 10, b is equal to 19, and c is equal to 12. Now we can substitute these values into our quadratic formula. So we have the formula again is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now we can plug in our numbers. So we have x is equal to negative b, so negative 19, plus or minus the square root of 19 squared minus 4 times negative 10 times 12 all over 2 times negative 10. So this is equal to negative 19 plus or minus the square root of 19 squared is 361 minus 4 times negative 10 times 12 is negative 480 over 2 times negative 10 is negative 20. So this is equal to negative 19 plus or minus the square root of 361 minus negative 480 is the same as saying plus 480. So the square root of 841, that's what you get when you add those two numbers together, over negative 20. So this is equal to negative 19 plus or minus the square root of 841 is 29 over negative 20. And now from this step, we're going to take this equation and break it into two separate equations because of this plus or minus. So we're going to have x is equal to negative 19 plus 29 over negative 20. And we're also going to have x is equal to negative 19 minus 29 over negative 20. Negative 19 plus 29 is equal to 10 over negative 20. Simplifies to negative 1/2. And over here, negative 19 minus 29 is negative 48 over negative 20. Our negatives will cancel each other out. And if we divide both the numerator and denominator by 4, we'll get 12 over 5. So the solutions to this equation are x equals negative 1/2 and x equals 12 over 5. Now that we have the two roots for x, we must interpret what they mean in the context of the word problem. Recall that x stands for seconds, measuring the amount of time it takes for the model rocket to hit the ground. Time is measured with positive numbers, not negative numbers. Therefore, the negative root of x does not apply to this scenario. Based on the positive solution for x, the amount of time that it will take for the rocket to hit the ground is 12 over 5 seconds. Great work! Hello, and welcome to this video about calculations using points on the coordinate plane. So first off, let's remember that a one-dimensional number line is a representation of all real numbers that extends infinitely in both the positive and negative directions and looks something like this. When two number lines intersect at a right angle at their zero coordinates, the two-dimensional coordinate plane is formed, which typically looks something like this. Generally, the horizontal axis is called the x-axis, and the vertical axis is called the y-axis. The point where the axes intersect is called the origin. Let's plot a point on the coordinate plane. The location of point A is given as a horizontal component x and a vertical component y, and written as x, y. From the origin, to get to point A, we would count 2 units to the right and 3 units up. So the coordinates of point A are 2, 3. Likewise, the coordinates of the origin are 0, 0. Since the coordinate plane is comprised of number lines, they can be viewed zoomed in or zoomed out as much as necessary to convey data or a story. For example, the x-axis here has been zoomed in. Because of the scale of the x-axis, the coordinate points of point B are 1/2, 3. And the x-axis has been zoomed in here, while the y-axis has been zoomed out. Because of the scales of the axes, the coordinates of point C are 0.2, 300. Using the coordinates of points on a coordinate plane, we can calculate the distance between 2 points. The distance formula, an application of the Pythagorean Theorem, looks like this. In words, it's the square root of the horizontal distance squared plus the vertical distance squared. In this case, the formula can be used, but since points A and D lie on the same horizontal grid line, all we need to do is count squares. This also works for 2 points on the same vertical grid line. The distance from point A to point D is 6 because the 2 points are 6 squares apart. Using the formula yields the same result. In this case, we can see that the coordinates of point B are 1/2, 3, and the coordinates of point E are 3/2, -6. In order to determine the distance between the 2 points, we'll need to use the formula because the points do not share a grid line, so we can't simply count squares to determine the distance. In this case, we're going to need to estimate the coordinates of point F because it doesn't lie at the intersection of 2 grid lines. It is often the case that we need to estimate the coordinates of a point. Let's estimate point F to be located at -0.4, -350. Now let's use the distance formula to get a good idea of the distance between points C and F. Using the coordinates of points on a coordinate plane, we can also calculate the coordinates of a point that lies exactly halfway between 2 points, which is known as the midpoint. The formula for finding the midpoint coordinates looks like this. In words, it's easy to remember as the average of the x's, the average of the y's. As we saw previously, the distance between points A and D is 6. Half of that distance is 3. Since points A and D lie on the same grid line, the midpoint will lie there as well, at the coordinates -1, 3. We can verify this with the formula. Even though we can always calculate half of the distance between 2 points, that won't tell us the coordinates of the midpoint in this example like the formula does. To graph, we'll need to estimate the location of -3/2. Previously, we estimated the coordinates of point F to be -0.4, -350. Let's use the formula to estimate the midpoint between points C and F. To graph, we'll need to estimate the location of -25. I hope that this video helped you understand how to perform calculations using the points on a coordinate plane. Thanks for watching and happy studying!